Okay, this is the fourth lesson for this week, and we are in chapter 13.3. And what we're going to be looking at in chapter 13.3 is what I mentioned in our first video. We're going to be talking about intermolecular forces. Once again, keep in mind that intermolecular forces are the forces between the molecules. They are not the forces that hold the atoms together, but rather, let's see if I have it here, the forces that would exist between the two ends of the molecule, between this blue and this pink. Those forces are going to determine the type of force that is there, and there are different types of intermolecular forces, will determine the strength of that force, and that determines whether it will be a solid, liquid, or gas, for instance, at room temperature. So I have up here, there's actually going to be two factors that are going to determine what a molecule will be. Say when it changes from being a solid to a liquid or a liquid to a gas. So up here I have a whole bunch of molecules which are all nonpolar, and they are called carbon chains. These are nonpolar molecules. They're tetrahedral or like a tetrahedral, but the hydrogens are all the way around the outside. So it's all positive around there. And this is their mass, 16, 30, 44, 58, 72. And the boiling point for methane is negative 164 degrees Celsius. So for us, that would be several hundred degrees below or 180 degrees below 0 Fahrenheit. In other words, methane's always going to be a gas. This is ethane, about half of that boiling point. Of course, that's in Celsius. We should really have these in Kelvin. This one is negative 42. Butane, which they put in lighters, it has a boiling point, turns into a gas at negative 1 degree Celsius. And then this is pentane, which is at 36, which is actually fairly high, like 110 or 120 degrees or something like that. Now, one of the things we're going to mention is as the size of the molecule gets larger, the molecules are going to actually move slower because kinetic energy depends upon the mass of the molecule. And the slower they move, the easier it is for the intermolecular forces to hold them together. And that's why this goes up as this mass increases. But now I have three molecules, methane, ammonia, and water. And all three of those have roughly the same mass. This is almost the same, 16, 17, and 18. They're all out of that second period. Goes carbon, nitrogen, oxygen. And the only difference is the number of hydrogens that they have around them. And look at the difference. Methane, negative 164. Ammonia, negative 28. But look at water's boiling point, 100 degrees Celsius. Something is going on there. It isn't just the mass of the molecule. There's something else that's taking place. And then finally, these ones are all molecules that look the same. This is oxygen. Right below it on the periodic table is sulfur, then selenium, tellurium. They all have this shape, a central molecule, either the oxygen, the sulfur, the selenium, the tellurium. Two hydrogens. It's a bent molecule, but look at your boiling points. Tellurium, which has a mass of 130, is at 2 Celsius. This one has a mass of 81, is at negative 42, mass of 34, negative 76, but this one a mass of 18, and it's 100 degrees Celsius. You would think that this would be even smaller than this one. So there's something else that's going on, and that's what I want to talk about, and it'll be in your book as well. The intermolecular forces that we are talking about, again, these are forces between molecules. And the forces are called either intermolecular forces, or sometimes these are called van der Waals forces. I don't know if your book uses that or not, van der Waals forces. And it turns out that there are three types of van der Waals forces, three types of intermolecular forces. The first one, in order of how common it is, well, I shouldn't say that. Let's do it this way. There's a type of intermolecular force called a dispersion force. Then there is a dipole-dipole force. And then there's something called hydrogen bonding. The dispersion force takes place between nonpolar molecules, and I'll explain that in just a minute. The dipole-dipole takes place between polar molecules, and the hydrogen bonding takes place whenever we have a nitrogen-hydrogen bond, an oxygen-hydrogen bond, or a fluorine-hydrogen bond. So water has a hydrogen bond. In terms of the strength of that particular force, the nonpolar is the weakest, the polar molecules are next, and the hydrogen bonds are the strongest. If we said that a nonpolar, and I'm not going to give a number with this, but the weakest had a number of about 1, the dipole-dipole forces would be approximately 10 times stronger, and actually usually like between 4 to 10 times stronger. And these ones are about 10 times stronger than these ones here. So this would be from 40 to about 100 times as strong. In fact, the hydrogen bond is so strong that it's called a bond rather than a force. It's strong enough that it actually really holds water molecules together. Now, the type of bond is absolutely critical. When we start talking about what affects when something will congeal and become a liquid or a solid, it's going to depend on the strength of this force. The stronger the force, the easier it is for the molecules to link up and to have that bond between them. But the other factor, so this is the first factor. So there's actually 2 factors. Factor number 1 is this one. What are the forces? Which force? But the second one, factor 2, is the size of the molecule. And as I already mentioned, what happens with the size of the molecule is that the bigger a molecule is, the slower it moves. The kinetic energy formula, which tells us our motion, is 1/2 mv squared. If the molecule is twice as big, it will end up having a slower velocity. It will move slower. So the size of the molecule matters. And what we would say is big molecules have lower melting points and boiling points, and small molecules, all else being equal, have a higher melting points and boiling points. And by the way, the same thing here. Hydrogen bonds, the strongest ones, these are the highest boiling points. And this one would be the lowest melting point and boiling point. So now we can come back to this table. Methane, and all of these are nonpolar. They all have dispersion forces between them. But because pentane is about 5 times larger than this, it has a much higher boiling point. Here we have methane, which has a nonpolar bond, ammonium, which technically has a hydrogen bond but not as strong as water. And because of that, water has the highest boiling point. Methane, which has dispersion forces, is the lowest boiling point. And on this one, these all have exactly the same geometry. They are all polar molecules. But The larger one, if we ignore that one, the larger one has the lowest or the highest boiling point. The smallest one has the lowest, but water, which has the hydrogen bond, has the smallest, has the highest boiling point. So let me take just a bit of time. And by the way, this requires some thinking. They're going to ask you questions. Which one of these has the higher melting point or the higher boiling point? And what we would be looking at, quite honestly, is they're either going to be, we have to look at what type of polarity it has, excuse me, and then we have to ask what's the size of the molecule. If they are the same type of bond, the larger molecule will always have the higher boiling point. If they have different types of bonds, if the size of the molecules are roughly the same, the hydrogen bond will always have the higher melting or boiling point. And by the way, it's easy for me to forget that you don't know this, but higher melting or boiling point means that it's something that we would see as a solid or liquid at room temperature, something which has a real high melting point would be a solid to us at room temperature. Something that has a real high boiling point would be a liquid to us at room temperature, and so on. So let me talk about how each one of the forces forms. Let me start first with dispersion forces. Dispersion forces take place between nonpolar molecules. Now, here's what happens. If I have, say, a hydrogen, we would say that the electrons that are shared spend as much, and there would be two of them, spend as much time around one atom as the other. However, every once in a while, you will have both electrons on this side, and as a result, this will be negative and this will be positive. And then just as quickly, it switches. And this hydrogen, the same molecule, would be where you would have the two electrons on this side. This would be negative and this would be positive. However, if you were to take and put, this is a little hard to visualize, but if you were to take a bunch of hydrogen molecules, what's happening is, although for roughly 50% of the time, you'll have a positive end and a negative end. And if you have another molecule next to it, when the two ends are opposite, there will be a temporary connection that's made. I like to think of this, and I do this in class if you were there. I get everybody up, and everybody is told to grab the shoulder of the person next to them, let go, grab somebody else. At any point in time, you have connections between all of the molecules. And that little bit of a connection is enough to eventually, when you slow it down enough, allow the molecules to form connections. And something like hydrogen, although it has a very, very, very low melting point and boiling point, it boils at just, I should have the number, but it's less than 20 Kelvin. But it still eventually will become a liquid and eventually become a solid. When you have the dipole-dipole forces, what you have with dipole-dipole, say something like carbon monoxide, that's the molecule that I'm using here, what we would say is that this side is partially positive, partially negative. That means that a large percentage of the time, this side is positive and this side is negative. And by the way, fully positive, fully negative. We say partial because it switches back and forth. So carbon monoxide, if I have a carbon monoxide here and a carbon monoxide here, most of the time this is negative and this is positive. And when that's the case, a bond forms. Now, to be honest, when it switches over, those two will actually push away from each other. The way magnets would. I have two magnets here, and the two magnets, if I get it too close, those are going to snap together. If I turn this around, they're pushing apart. So carbon monoxide, most of the time, is being attracted. I know that's kind of hard to see, are being attracted, but a small percentage of them are actually pushing apart. But if you go back to that same analogy I just gave, if I said in the room, I want you to grab the person next to you, hold on to him for 3 seconds, then push them away, grab somebody else for 3 seconds, we would have a lot of connections, and that would be equivalent to having bonds which hold that together and make it into a liquid or a solid. Now, with the hydrogen bond, and we'll end with this, but the hydrogen bond, if I take oxygen and hydrogen, remember that hydrogen is a single atom. It's a nucleus, a positive, with a single electron going around. When you take oxygen and hydrogen, and let me do it this way. Let me take and put, there's 8 positives here. And here we have our positive, and we're sharing this electron. But most of the time, the electron is here. So this is the key on hydrogen bonding. What happens when this electron is with the other side? We now have this being negative. When that's gone, all that's left is a positive charge. And that positive charge will be attracted and actually get real close. What happens with water molecules is that water molecules, when the hydrogen has given its electron to the oxygen, this space here is almost like a little proton stuck onto the oxygen. And as a result, the water molecules can get much closer together. And that is the key. I have my 2 magnets here. If I play with these 2 magnets, when I get it to right about here, I can start to feel it pulling. Right here, I don't even know that those are magnets. Here, I can just barely feel it. But if I get it too close, I can't even keep them from getting, and I'm strong, I can't even keep them, I'm joking, I can't even keep them from touching each other. What's happening with this, if you think of this as the oxygen and this is another oxygen, and they both have their electrons from the hydrogens, these two are able to get real close, and it forms a very, very strong intermolecular force. It really is how far away the molecules are from each other. So rather than something like this, where I have another oxygen that would be attached like this, what's actually happening is something more like this. And because this distance is real small, the force is greater. And that force is called a hydrogen bond. And it turns out that the only time, like we said, that the hydrogen bond exists is whenever you have oxygen, hydrogen, nitrogen, and carbon, fluorine hydrogen. What's interesting is this oxygen, hydrogen, you don't know this yet, but something like alcohol, the alcohol you have in your medicine cabinet, maybe if you can buy it, it's hard to get a hold of right now because of the virus, is C3H7OH, which means it's carbon, carbon, carbon. Hydrogens, by the way, those are essentially this is like a non-polar end of that molecule, but then we have oxygen, hydrogen. And this right here means that alcohol is going to be a very polar molecule with hydrogen bonds. So that's pretty quick to go through this. I'll spend some time with you on Wednesday probably talking about this. But what I'd like you to do is read section 13.3. And then we are going to try problems 19 through 28 all. A little bit longer assignment, but this is actually a fairly important part of this chapter is to understand those bonds. So you can also look it up online, look up intermolecular forces if you're struggling with it, and I'm sure they'll be able to help you in other places as well. All right, that finishes this week, and this will all be up on Schoology. So we'll hope to see you soon.